Hello, and welcome back to more functional analysis. I'm Fabian, and together we're going to review a video from the bright side of mathematics. This video is on examples of metric spaces, and together we are going to complement these examples by counterexamples. So examples of mappings that appear to be a metric, but aren't because they fail to have one of these properties. I think having some counterexamples at hand will increase your understanding and intuition, because for every property, every defining property of the metric, you also know a mapping that does not have this property. So let's start.
We've already learned if we have a set X and a metric for this set, then we call this a metric space. In a metric space, one can now generalize a lot of notions you may know from a real analysis course. For example, we can define sequences, limits, accumulation points, and so on. Of course, this is what we will use a lot in this series.
So, before we dive into the examples that we are going to see in the video, let us quickly recap why we are doing all of this. So as already said, we want to talk about sequences, accumulation points. So to sum up, we want to talk about approximation of objects in infinite dimensional vector spaces or other types of sets. For this, we will need a notion of distance first to really quantify what it means for two objects to be close to each other. And the mathematical term for this is, as you may have already guessed, the metric. And having a metric or a notion of distance at hand will then later on help us to define approximation processes via convergence. As a quick recap, let's also go through the names of the three properties that define a metric. The first property was definiteness and tells us whether two objects that have distance 0 are equal or different. The second property is called symmetry. Symmetry tells us that the distance from A to B is the same as from B to A, which may also coincide with your natural intuition you have when talking about distances. And the third property is the property of the triangle inequality. The triangle inequality, loosely speaking, tells us we cannot get to a shortcut by taking a detour. Let's take a look at the first example.
However, before we do that, let's talk about some examples. So let's start with a simple one, which is also one of the most important ones. The set is just the complex numbers, and the metric should be the usual notion of measuring distances in the complex numbers, which means it's the absolute value where we look at the difference of both points. Now, the visualization in the complex plane gives us indeed the normal geometry we have in the plane. If we pick two complex numbers x and y, we know we can calculate the difference, which is a new complex number. And the length of this new complex number is exactly the distance we want. Now you know.
So this example talks about complex numbers, and you know that we can visualize complex numbers also in R2, in the plane that we see here on the right hand side, having the real part on the x-axis and the imaginary part on the y-axis. So I promised you some counter examples, but let me also add a little bit to this example A by telling you, well, you also know another very classic metric on the real numbers that is defined in the same way as here, but it's not in R2. So basically this is just a difference of two real numbers and then taking the absolute value. And you may see from this definition already, this definition is symmetric. If the absolute value of a number is 0, then the number itself needs to be 0. So this is also definite. And the triangle inequality is, well, just the triangle inequality that we have for absolute values.
So this normal geometry we have for measuring distances, you can also do in higher dimensions. For example, if the set is Rn, we would have a standard metric we can choose, and this is usually called the Euclidean metric or the Euclidean distance. And because you know Pythagoras' theorem, you also know the definition of D. It's just the first component of x minus the first component of y squared plus the second component, and so on until you reach the last component, which is xn minus yn squared. And then, of course, we need the square root. Okay, so this is the Euclidean metric, the common but only a possible choice of a metric in Rn.
So let us look at this example a little bit more closely. So let's specify the dimension of our space, and let's say x equals R2. Then the Euclidean metric, which I denote with a small e in the subscript, of 2 points x and y, is defined as the sum of the difference of the squared absolute values of x1 minus y1 plus x2 minus y2. And then, of course, we also need to take the square root here. So, as said in the video, this is a very classic choice, and it is a metric, so it fulfills all three properties. One question you may ask yourself is, why do I need the sum here? Wouldn't it suffice to just take one of the vector's components and look at the difference there? Well, let's see. Let's define a further metric, or let's try to define a further candidate for a metric that we call dE with a tilde. And dE tilde of x and y will just be, well, just the first part of the Euclidean metric. So this will be the square root of x1 minus y1 squared. So you see the square root and the square here cancel out, so it's just x1 minus y1, which is the usual metric that we also have in the case of real numbers here. But now we are taking on the first components of our vector. Just to make sure, if x is an element of R2, I can write x in the form x1, x2, where x and x1 and x2 are elements of the real numbers. So you see, linear algebra is handy here. We already know what to look at when we have a vector like this. Same goes for the vector y. It has two components, y1 and y2. And now our new mapping, dE tilde, is defined as the absolute value of the difference of the first components. Let's look at an example in the plane. Let's say we have two vectors, x and y. X is up here and y is down here. So then the first component of x I can read off on the x-axis here, and this is the component x1. Same goes for y. So the first component of the vector y is called y1, and this is the component I find here. So now the difference between, or the distance between x and y with this new metric dE tilde, so we do not know whether it's a metric or not, so with this candidate for a metric dE tilde would be just the distance between x1 and y1. So calculating the distance between the first components here. So what we see here, the length would be dE tilde of x and y. So what you can see already from the definition and now also from the sketch, dE tilde completely ignores that our vectors x and y are two-dimensional. They have a further component, and our mapping dE tilde ignores that. So you may have already guessed that this will affect also the metric properties that we would now have to check. So the question is, does dE tilde define a metric or not? So let us start with an easy observation here. So we have three properties to check: symmetry, the triangle inequality, and definiteness. Let's do it in precisely this order. Let's start with symmetry of dE tilde. So for this, we just take a look at dE tilde of two vectors x and y. By definition, this is nothing else than the absolute value of the difference of the first components. And now we can use symmetry of the metric that is induced from the absolute value of real numbers. So this is the same as saying y1 minus x1. And by the definition of dE tilde, this is nothing else than dE tilde of y and x. So if we look at the left-hand side, we have dE tilde of x and y, and on the right-hand side we see that this is equal to dE tilde of y and x. So symmetry has been checked. The second of three properties that we need to check is the triangle inequality. So for this, again, we need x and y, and we also need a third vector. So let's say x, y, and z are elements of R2 with components x1, x2, y1, y2, z1, z2. What we need to show is that dE tilde of x and z is less or equal than dE tilde of x and y plus dE tilde of y and z. Yeah, so imagine that there would be a third point somewhere here. Let's call it z. Then the triangle inequality tells us the distance from x to z will be smaller, also less or equal than the distance from x to y and from y to z. Yeah, so I cannot get to a shortcut by taking a detour of a further element. Yeah, so the direct connection should always be the shortest. How would we prove this? Let's make some space. So by definition, dE tilde of x and z is nothing else then the difference of the first components. So absolute value of x1 minus z1. Now we do a popular trick in this type of proofs. We add a 0, and in our case the 0 that we add is precisely the element y that we also need here. So what we add now is minus y1 plus y1. So this is the 0 that we have. And now we use the triangle inequality that we already know for the absolute value. So you see, knowing about the absolute value really pays off in these types of proofs. So we use the triangle inequality for the absolute value. And we get x1 minus y1 plus y1 minus z1 by the triangle inequality for the absolute value. Checking again with definition of dE tilde, we see the following. We have the difference of x1 minus y1 here. This is nothing else than dE tilde of x and y. And the second summand is y1 minus z1 absolute value. This is the same as dE tilde of y and z. So in fact, we can even write an equal sign here. And we have shown that dE tilde also fulfills the triangle inequality. So now let's come to the third of 3 properties that we need to check for a metric, which is definiteness. So for definiteness, we need to show an equivalence. Let's recall the equivalence for definiteness. It tells us that for all x and y of our space R2, we have that d of x and y equals 0 if and only if x equals y. All right. How would we prove definiteness? We have an equivalence. That means we have 2 things to check. The first equivalence that we are going to check is the easier one, I would say. Yeah, if x and y are equal, then also the metric, or our candidate for the metric, equals 0. So let me also add that we want to do this for dE tilde. So if x equals y, recall the space that we're in, it's R2. When are 2 vectors equal? Linear algebra tells us 2 vectors are equal if the components are equal. So this means x1 equals y1 and x2 equals y2. Just by knowing the space from linear algebra. Equality of vectors means equality of all components. All right, then in the next step, let's calculate dE tilde of x and y. So dE tilde of x and y is defined as the absolute value of the difference of the first components. But as we saw, x1 equals y1, therefore x1 minus y1 equals 0. So we have shown that if x equals y, then also dE tilde of x and y equals 0. So the left hand side here. All right, what about the other direction? Does the other implication also hold? So for this, let us first take a step back and think about the following example. So let's look at two vectors. And clearly this vector 1, 0 is not the same as the vector 1, 1. Why are they not the same? Well, two vectors are different in R2 if they differ in at least one component. The component in which they differ is the second one. So here we have a 0 and here we have a 1. Therefore, our two vectors are different. So what about the distance between these vectors? Let's calculate it. dE tilde of 1, 0 and 1, 1. How do we do this? Well, it is defined as the difference of the first components. So what I need to do is I take the absolute value of the first component minus the second component. So you may have already seen it. The result here is 0. So I have two vectors that are different, but still dE tilde, which we want to check if it's a metric or not, equals 0. Therefore, the equivalence above, or at least the implication from the left-hand side to the right-hand side, cannot hold. So, in conclusion, we can say that dE tilde is not a metric. Yeah, so definiteness is not fulfilled. But our mapping dE tilde still fulfills the symmetry property, it fulfills the triangle inequality, and mappings like this come up very often in functional analysis, and they have a special name. So even though it is not definite, so it is not a metric, we still call things like this a pseudo-metric. So dE is not a metric, dE tilde is not a metric, but dE tilde is a pseudometric on R2. Yeah, pseudometric means it is not definite. And examples like this, yeah, you have seen one easy example, so it comes from ignoring one component that is crucial for differentiating two objects. Another example you may know from your course on measure theory and integration theory is the LP metric on spaces of measurable functions. Let's take a look at the next example from the video.
So please remember, for a metric we only need the three properties. It should be positive definite, symmetric, and fulfill the triangle inequality. We already know that these two fulfill the three properties, so they are metrics on Rn or C respectively. So let's look at another distance function we could define for Rn. This would be the maximum, and then we look at the difference x1 minus y1 and use the normal absolute value or modulus in R. So let's write it down for all components, which means we want the maximum of all these differences. In fact, this is of course a metric as well. It's not hard to check that it fulfills our three properties, and most of the time only the triangle inequality needs some work. However, However, we should first visualize the whole thing, maybe again in the plane.
So we're going to skip this visualization, but I'm going to give you a quick mental exercise, because you may see that this second metric is of the same structure than the first one. So you can think about the following. So a quick mental exercise. So why does let's say d max tilde of x and y, which is defined as the maximum of let's say the difference of the first components and the second components, not define a metric on R3. Yeah, so vectors that have 3 components, x has components x1, x2, and x3. Why does d max tilde, which is defined, well, just like the one here, but we leave out the last component, not define a metric on R3?
So here we see 2 points, x and y, and what we now have to do is calculate the distances of the components here. Now in blue we have the distance in the first component and in green in the second component. And as you can see, the blue one is bigger, so the maximum is indeed this number here. Which means using this metric, this is exactly the distance between x and y. Or in other words, if you choose a point z here, for example, it has the same distance from x than the distance x to y. Of course, this shouldn't be so surprising. Of course, you could have different points that have the same distance from a chosen point x. In our Euclidean metric from above, or in a picture in a complex plane, this would be just a circle around x. However, with another metric, such a thing we could call a circle might look completely different. Okay, so please keep that in mind whenever we use circles to visualize things. For our last example here, let's choose a more abstract one, just any set x, which should not be the empty set. Then we define a metric by distinguishing 2 cases. The first case is just x is equal to y, and the second, of course, x is not equal to y. By the first property of the metric, we already know here we need a 0. However, we are not allowed to have a 0 here, so we can choose whatever we want, and most of the time we just choose 1. Okay, so let's check together that this is indeed a metric.
So we're not going to watch the check of this metric, but we're going to do something different that I personally feel very helpful for you to understand how this metric works. And if we want to understand a definition, it's always a good idea to modify it a little in order to see whether it still works or not, to find out which parts of the definition are really crucial and cannot be changed. And this is a very simple definition. And so it should already be minimal. We should not be able to change a lot about it. So maybe let's first start with the good news. So thanks to the discrete metric, which works on any set, so every set can become a metric space. Yeah, so given just a set that is not empty, you can already make it a metric space by using the simple definition. But as a quick mental exercise, think about the following. What would happen if we would say x is not the empty set, and we define d of xy to be 0 if x equals y, and also 0 if x is not equal to y. So is, let's call it dd for discrete tilde, still a metric? Yeah, you can ask yourself this, go through the properties, check also the proof that is in the video from the bright side of mathematics if you have any questions. And as a further addition, you can also ask yourself, is let's say dd double tilde, where we set it to 2 if x is not equal to y, is this still a metric? Yeah, so we have two quick exercises that you can also do in order to understand why we need the numbers like they are here. Yeah, and you already may see a procedure that you can apply to other definitions that you encounter. Don't take anything for granted. Really try to play a little with the definitions to see how it works and how it doesn't. So, I promised you further counterexamples today. And so far, we saw one example of a metric, or a candidate for a metric, that fails definiteness or positive definiteness. So we still have two other properties to check, and I will give you also two further examples of metrics or candidates for metrics that do not fulfill one of these properties. So let's jump into the symmetry. Recall the good news from before. Every set can be made a metric space. So in particular, we do not need the vector space to get to a metric space. We can also just take a set. And the set that I want to make a metric space now is just the unit circle that we call S1. So this is a subset of R2, and as such, it's not empty. So using the discrete metric, we can make it a metric space. But now I do not want to use the discrete metric. I want to use another metric that, for the sake of simplicity, I just call DC for clock. So how does this notion of distance work? So we have a circle, and let's say we have one point here, which is the point x, 1, 0, and we have another point here, y, which is 0, 1. Yeah, so imagine this just as parts of the real line. All right. So now our new mapping should give us the distance between two elements on the unit circle by taking the shortest clockwise path between x and y. So how is this to be understood? So think about a clock. Then let's say our clock points to 1, 0 here, and we now want this pointer to run in a clockwise fashion, so in this direction, until it hits y. So, of course, our pointer runs along this path here, yeah? So our set is the unit circle, so we can also calculate the arc length of it. So in our example, x and y, the distance of the shortest clockwise path between x and y would be 3/2 pi. Yeah, so the full length of the circle's circumference would be 2 pi, but we only use 75% of it. So it's 3/2 pi. So what about now the distance between y and x in the above example? So recall that we go through our circle in a clockwise fashion. So if I now start at y, well, and I want to go to x, then the shortest clockwise path will run like this. Yeah, until I hit x. So in this case, the connection, or the length of the connection, is just this shorter path here. So I need to run in the clockwise direction. So I only need to run a length of 1/2 pi. And we see, of course, 3/2 pi is not the same as 1/2 pi. So in this case, we have now a notion of distance that makes sense if we, for example, are only allowed to run in a certain direction. But you see that this addition of the direction in which I measure the distance here already breaks down one of the important properties that the metric has, which is symmetry. So this d-clock tilde is not a metric because it's not symmetric. But still, things like this occur, and we have another name for this. So we call this a quasi-metric. It's not a metric, but it's a quasi-metric. So you may say, all right, I have something that is a quasi-metric. Can I symmetrize this mapping? And yes, there is a possibility to symmetrize a quasi-metric. So given a quasi-metric, can I derive a new metric from this that is indeed symmetric? Yeah. So this will be the next point that we talk about. So symmetrizing a quasi-metric. So, and one way to do this would to say, well, let's define d-clock of x and y by the arithmetic mean of d-clock tilde of x and y plus d-clock tilde of y and x. So you may think, y is the 1/2 here. Could we just take the sum? Think about it like this. If my quasi-metric would already be symmetric, then d-clock tilde and of x and y would be already the same as d-clock tilde of y and x. So I would have 2 times d-clock tilde of x and y. Dividing it by 2 does not give me anything new. But in the case that I have a quasi-metric that is indeed not symmetric, like the clock quasi-metric that we just discussed, then this will give me a new metric that is indeed symmetric. This procedure you may also recall from linear algebra. If you have a matrix that is, well, not symmetric, so the transpose of the matrix is not the same as the matrix itself, by taking the arithmetic mean of the matrix and its transpose, if it's a quadratic matrix, of course, then we get a symmetric matrix. So the structure of what we do here, of this symmetrizing procedure, you may already know from linear algebra, and it finds also application here in our setting of symmetrizing a quasi-metric. So we have now an example for a quasi-metric, so a mapping that is not symmetric. We have also an example for a notion of distance that does not fulfill the positive definiteness or the definiteness part. So now for the last example, or the last counterexample that I want to share with you today, let's talk about the triangle inequality. And for this, I would like to recall once again the Euclidean metric that we had. So the Euclidean metric on R2 was defined by saying the distance, so let's say x is R2. Then the Euclidean metric of x and y was defined as, so outside I have a square root, and I take the sum of x1 minus y1 squared plus x2 minus y2 squared. So this was the Euclidean metric. So we can generalize this by changing the exponent. Yeah? And what we're going to do is we are now looking at the metric dp of x and y. Yeah, we're still on our space R2. And so the way we are going to do this is I'm going to show you what we change now. So we want to change the 2 here and write a p here, here, and here. And what we have defined here is, well, a generalization of the Euclidean metric, and this is a metric for values of p that are smaller than infinity and greater or equal than 1. So with similar techniques as you use for the Euclidean metric, so you also need a Minkowski inequality and so on, you can show that this defines a metric on R2. And of course you can also generalize it to higher dimensions. So if you take the sum over all components of an n-dimensional vector, in this fashion you get also a new metric, and you have also something similar on function spaces and of spaces of sequences. So this is really a large family of metrics that you have in classical spaces of functional analysis. Today's topic is not further examples, it is counterexamples. So one way to generate counterexamples is also to really challenge the boundaries in which our definition holds. What do I mean with boundaries? So we have here 2 boundaries for which my statement holds. Yeah, so dp is a metric for p greater or equal than 1 and smaller than infinity. So of course we cannot plug in infinity here, but you may also know from either a course on multivariable calculus or also measure theory that there's also an infinity metric that instead of a sum just is the example that we saw in the video. So this is the maximum of the differences of the first component and the second component. So, and one way to see this is via a limiting process, so letting p go to infinity. This is also a classical example of what we are interested in when we do analysis. It's a limit, and if we have something that is bounded, the question is always, what happens if I run towards the boundary? What does change? So now there's another boundary here, but this is including the boundary. So 1 is also the case here. Yeah, so if I plug in 1 for p, then I get just the sum of the absolute values. So the 1 metric, also a very classic one. But why can't we plug in other numbers here? So why does this definition end? So let me write down this question. So what about, let's say 0 less than p less than 1. Let's say p equals 1/2. Yeah, 1/2 is a number between 0 and 1, and it's clearly less, so it does not fit this definition here. So we would expect that this does not define a metric. So the question is d 1/2 of xy defined as here above? So I'm just going to copy it. So x1 minus y1 now to the 1/2 plus x2 minus y2 to the 1/2 to the 1 over 2, so squared. Is this a metric? So I can already give you the answer before we dive into the proof. So the answer is no, but it is a semi-metric. So what is a semi-metric? It fulfills all properties of a metric except for the triangle inequality. So what we are now going to find out, how does the triangle inequality, or well, what kind of property does this specific type of distance have that comes maybe close to a triangle inequality but is not the triangle inequality. So for this, we are going to first look at the small lemma that deals with inequalities. So let's say we have two numbers, a and b, that are greater or equal than 0. So then we have three types of inequalities, which I write down here quickly. So the first one is to say that a plus b to the 1/2 is less or equal than 1 to the 1/2 plus b to the 1/2. So this is the first inequality. The second inequality that we will need for this is that a plus b to the 2 is less or equal than 2a squared plus 2b squared. And the third inequality is that 2ab is less or equal than a squared plus b squared. Yeah, this is a lemma for real numbers. We will see how it goes into the proof of showing that d 1/2 is indeed a semi-metric. So this is a nice calculation with real numbers. So we do not need a lot of tools to it. It should be very nice. Let's start with the first inequality. For a, b greater or equal than 0, show this inequality. So if a and b are greater or equal than 0, then of course also the product a to the 1/2 times b to the 1/2 is greater or equal than 0. So now we can calculate a plus b to the 1/2. No, let me start differently. So a plus b is then of course smaller than a plus a positive number, which we say is 2 to the a 1/2 b 1/2 plus b. Yeah, so what I did here was I just took this, which is greater or equal than 0, multiply it by 2, it's still greater or equal than 0, adding something that is greater or equal than 0 to something can only make it bigger. But now, well, we know the first binomial formula. This is nothing else than a to the 1/2 plus b to the 1/2 squared. On the other hand, a plus b is nothing else than a plus b to the 1/2 times 2. Okay, now taking square roots on both sides gives us 1. Inequality 1. Yeah, taking the square root here gives me a to the b, a plus b to the 1/2. So this is the right hand side. And also here taking the square root gives me the right hand side. Nice. Let's do the second. Let's do the third inequality first. So for this, we use another binomial formula, a minus b squared. As it is a square of real numbers, this is greater or equal than 0. And on the other hand, well, the formula tells us this is a squared minus 2ab plus b squared. All right, now I just rearrange the formula. So 2ab goes to the other side. And then I see I have a squared plus b squared on the right hand side and ab on the left hand side. So inequality 3 is also very quickly proven. So for the last inequality that we need to prove, we do the following. So we start with the first binomial formula, a plus b squared. So this is also the left hand side of our inequality. Then we see that this is nothing else than a squared plus 2ab plus b squared. This is just the definition. Then we know that 2ab from part 3 is smaller than a squared plus b squared. So this is smaller than a squared plus, so now comes our third inequality, a squared plus b squared, which is the right hand side of the second inequality. So this is 2a squared plus 2b squared. So easy proof, real numbers. Now we need to use this result of the lemma for our actual proof. Yeah, so what do we want to prove? We want to prove that d1/2 x minus d1/2 of x and y defined in the following way is really a metric. So going to copy this information. Let's get started. So the first thing that you may check in here is, well, definiteness won't fail. You can do it in the same way you did it for the other metrics or for the Euclidean metric. It is definite. And of course, if you look at the definition is also symmetric. So d1/2 is also symmetric. So we are only going to look at the triangle inequality and see what we can derive here. So for triangle inequality, let's write it like this. So triangle inequality. Yeah, it won't be a nice inequality like you know. It will be a little bit different. So for this we choose x, y, and z, 3 elements of R2. P is 1/2, and let's write down. So d1/2 of x and z equals, so now I use a very big bracket here for the outer part. So we have here the 2 above. For reasons of symmetry, let me also make this bracket a square here. It's always good to have different types of brackets so you know which ones are the ones that match. And the definition is x1 minus z1 to the 1/2 plus x2 minus z2 to the 1/2. So the first thing that we're going to use again is the triangle inequality for the absolute value. And how are we going to use this? So we have a absolute difference of absolute values here, and we can write this as x1 minus y1 plus y1 minus z1, just like we did in the prior proof, and then use this inequality by writing this part here. But now with the triangle inequality, this gives us, well, a sum of 2 elements. And of course, I cannot forget about the 1/2 outside. This is a square root function. The square root is strictly increasing. This means if my argument gets bigger, also the function values gets bigger. So this is the second thing that we use here. So we use the triangle inequality and then monotonicity of the square root. All right, so we do the same for the second part here. So for the second components, so I'm just going to write this down below. So here we have x2 minus y2 plus y2 minus z2, 1/2. And then I need to close the outside bracket with a square. Perfect. So now let's see how we can use our lemma from above. So this here was our green inequality, and we can see this inequality may be applicable here as well. So we have a sum of positive numbers, and we have a square root bordering this sum. Yeah, so we mark it more clearly. So we have here an A, and we have here a B. So we are now going to say, well, you are going to be my positive number A. It's positive because it's an absolute value, and the absolute value only takes positive numbers. And we are going to take you as a B. Well, then the square root of u to the 1/2 is going to be less or equal than the sum of the square roots. So I'm going to write this down. So now this is less or equal than, so let's not forget the outer bracket, x1 minus y1 to the 1/2 plus x2 minus y2 to the 1/2. So this is by 1. And I do this, of course, also for the second part. So this is also smaller than x2 minus y2 to the 1/2 plus y2 minus z2 to the 1/2. So, and of course, I do not want to forget about this large bracket in the end. So I also close this bracket here. Okay. So now I take a look at the second inequality that I proved. Here we have again two positive numbers a and b and a square root outside. So we have a square root here outside. And now I'm going to take again two positive numbers a and b. And now I'm going to say that, well, u are my positive number a and u are my positive number b. So now applying the second inequality will give me the following. So let's first write down the greater structure that we have here. So I have the square outside. So I have a square here. And I also need a 2 in front. And I also have another square for the b with a 2 in front. And then what about the inside? So the inside I'm just going to copy. Going to copy and rescale it so it really fits. So this is the first part. And the second part is just copy and pasting what I have already done. So, but now let's take a quick look back how our metric d was defined. It's just the square of the sum of two square roots, which is what I have written down here. So I can now use the definition of d 1/2 tilde to see that this is just 2 times d 1/2 tilde of x and y plus 2 times d 1/2 tilde of y and z. So let's zoom out and have the bigger picture again of this a little bit technical proof, but well, sometimes it is like that. We need to get our hands dirty with some calculations, but I hope you saw that this is just real analysis that we did here, nothing fancy going on. So we started out with d 1/2 of x and z, and we showed that this is less or equal than, okay, the sum of d 1/2 tilde of x, y, and y, z, but with a prefactor in front. So in the usual triangle inequality, we have a 1 standing here, but as I already announced, d1/2 is not a metric. So, and the triangle inequality is failing, so it's just a semimetric. But I think it is still, well, it's still useful to know this because it's not too far away from a usual triangle inequality. You just have to keep in mind there is a prefactor here. So let's close with a nice picture, because something that relates to notions of distances in a metric space is the way that unit circle looks. And as already was announced in the video, the unit circle might look a little bit different from what you may expect. So again, S1 should be is now well, the unit circle, but I'm going to define it depending on the metric that we use. So, and I want to denote the metric here below as well. So this now should be the set of all x of R2 with the following property. I want the distance dp of x to the center of my circle to be exactly 1. Yeah, so everything laying on the boundary of a curve. So let's take a look, and let's start with the circle that we all know. Yeah, and this is the circle that comes from the Euclidean metric. So if I plug in p equal to 2, so this is not centered yet. Let me center the circle also. Hope this is more or less centered. So this is the circle I get if p equals 2. Yeah, the Euclidean metric, we get really a circle that we know. So if we now choose p to 1, this you may also easily calculate, then our circle looks, well, not round anymore, it gets corners. So the circle that we get, it looks now like this. Yeah, so this is all the points where the sum of the differences of the components in the absolute value is 1 here. So if we let now p go to infinity, our circle also looks a little bit different. It is still a square, but it now looks like this. Yeah, so it should be a perfect square here, but yeah, you get the idea. So you see that we start out with 1, then we get to a circle, and then the circle gets to a square. Yeah, if you follow the trajectory here, for example, you follow a point here, yeah, then it's like our circle is bending to the outside. So what about the semimetric that we just discussed? So for p1/2, well, this direction is already taken up. So what will happen is the circle will bend inwards. Yeah, and we will get something that looks like this. Yeah, it's some kind of, yeah, it looks like it's mirrored along an axis. But the most important thing to see here is there is a fundamental difference between values of p that are greater or equal than 1 and the ones that are strictly smaller than 1, which is convexity. Yeah, so if I just look at the portion of the circle that is bounded by this yellow curve, I see the interior is not convex anymore. So yeah, this is what happens, and this is how you can also interpret the fact that we do not have a nice looking triangle inequality anymore. That's it for today. We can close this review. Thank you very much for watching. I hope you learned something new today. If you did, please let me know via the like button. If you have further comments, suggestions for improvements, further examples or videos that you want me to cover, let me know in the comment section. I'm already looking forward to it. Have a nice day.